Hello and welcome to my presentation on the Metaheuristic optimization of radio interface constrained channel assignment in a hybrid Wi-Fi dynamic spectrum access wireless mesh network. I am Natasha Zlobinsky, and my supervisor, co-supervisor, and co-authors are David Johnson, Amit, Mishra, and Lysko. Quick word map of this talk. I will start with an introduction and background, then present the network model and scenario considered in this work. This brings us to the problem statement and the assumptions made in addressing this problem. I will then present an algorithm that we developed to generate candidate solutions that are feasible for use in the Metaheuristic optimization algorithms. The implementation choices for those Metaheuristic algorithms, simulated annealing and genetic algorithm, are discussed next. I will then present the simulation results before concluding. According to internetworldstats.com, internet penetration in Africa is only 43.2% versus 65.6% worldwide. According to Statista.com, worldwide rural internet penetration is only 38% versus 72% in urban areas. Therefore, rural areas in Africa are expected to have an internet access problem. However, even for those with internet access, and increasingly in developing countries, especially in Africa, the problem is not so much that internet access is entirely absent, but that it is expensive and unreliable. On the technology front, wireless mesh networks introduce redundancy and so can improve reliability. They can aggregate demand and so lower the cost of access, and extend internet access from an internet gateway to a much wider area than can be reached directly. However, wireless mesh networks generally use Wi-Fi, and Wi-Fi requires line of sight and has limited propagation distance. Several new dynamic spectrum access bands are being opened worldwide for unlicensed access. Some examples are Citizens Broadband Radio Service and Wi-Fi 6E 6 GHz. Television white space is one of the bands that has been around for longer. It is especially interesting for our application of rural and outlying areas because of its superior propagation characteristics, having lower frequency. For example, it does not require line of sight and has much longer ranges. So a possible remedy for our access problem in these scenarios could be to combine dynamic spectrum access with wireless mesh networks. A hybrid or multi-band wireless mesh network can improve link diversity and opens new avenues for research. The fact that those bands will be accessed without requiring a license can also reduce cost. Here we present the scenario considered in this work. The blue dots represent our TV white space mesh nodes. Each of these mesh nodes has a minimum of 3 interfaces. 2 are for the dynamic spectrum access, in this case, TV white space mesh links. And then 1 is the access point interface on which connection is given to the end users or clients. There is an optional additional Wi-Fi interface that can also be used for mesh links. And this is in case there are not enough available channels on the DSA band. Our spectrum nodes are in the presence of the primary users, which in this case is TV broadcast services. For this reason, in order to prevent interference with the primary users of the spectrum, it is required that our nodes use a geolocation spectrum database to obtain the list of allowed channels and operating parameters. Our nodes are also in the presence of other secondary users that may also be accessing this spectrum band opportunistically. So let us consider that the gateway node makes a query to the geolocation spectrum database and finds the list of allowed channels. It senses its environment and chooses this blue channel. Let us call it channel 1. It sends out beacon frames on this channel, which enables the first hop nodes to join the network on that channel. However, if we then want to expand the mesh to include these nodes over here, channel 1 may no longer be able to be used because these secondary users might also be using that channel. One option would then be to switch over the mesh to the next available channel. In this case, we could call this red channel channel 2. However, a more optimal solution might be to keep these links on channel 1 and only assign channel 2 to some of the links. As we can see, there are many different combinations of mappings of channel to link, and some may be more optimal than others. This brings us naturally to the research question: how to allocate channels to the mesh node radio interfaces optimally according to certain metrics, which we will define. So this problem has two main issues. The first is that we need to minimize interference within the network and externally. The second is that this has to happen while ensuring connectivity of the mesh network is maintained. These two requirements are somewhat contradictory. On the one hand, to minimize interference, we may model the network as a graph and map this to a conflict graph, and then simply minimize the number of conflicts. But in this way, we would not ensure that connectivity is maintained. And so we have to identify links and make sure that connectivity is still maintained on those links. Also, different channels are allowed for use by different nodes. They experience different levels of external interference and different channel conditions. All of this adds to the complexity of the problem. So our goal is to optimally assign or map channels to a set of links. That is to find a channel assignment that is optimal or near optimal. We have chosen to optimize on the average SINR. This is because it encompasses both the requirements to minimize interference, which we have because of this I interference in the denominator, but also maintaining connectivity by maximizing the signal strength at the receiving end of all required links. We ensure that the signal is above the receive sensitivity at each receiver, and this enables the signal to be decoded correctly. There is an interrelationship between routing and channel assignment. However, our channel assignment will be done on a much slower timescale than routing, and so will be applicable to a number of different routes. Hence, we do not need to consider routing further in this particular work. So, more formally, we aim to find the channel assignment A that minimizes the inverse of the average SINR, averaged over all the nodes V in the network. This bar indicates that each SINR at node V is in fact an average itself of a number of samples. This objective is subject to the constraints where the number of assigned channels for each node V must be less than or equal to the number of radios at that node. The set of assigned channels has to be a subset of the allowed channels at each node V. And the signal has to be above the receive sensitivity at each receiving node for it to be able to be decoded correctly. Some assumptions that we make. The first is that nodes are stationary and the gateway node knows their locations. The mechanism by which these locations are shared is not within the scope of this work. We also assume that nodes are broadly in the same geographical area, and that the considered set of channels for the assignment is the intersecting set of allowed channels of all nodes. We make this assumption about nodes being in the same broad geographical area so that there is an intersecting set of allowed channels. Larger networks can be partitioned into clusters that do have enough overlapping channels. We also assume that channel widths are fixed, and Since we optimize on the average SINR perceived by nodes, we assume that this measurement is accurate enough. We do not take into account hardware issues with the sensing, but we assume that any temporal issues would be averaged out by using a large number of samples. We also assume that links are traffic saturated. So here we present the new algorithm that we developed for ensuring that the solutions that are sampled by the metaheuristic algorithms are all feasible. Each of these solutions is a channel assignment, which will be used in the metaheuristic algorithms. So for each link in the set of links L, if the number of assigned channels at a node is less than the number of radios at those nodes, then we can choose C randomly from the set of intersecting allowed channels of those two nodes. If one of the nodes already has the number of channels assigned as it has radios, we then have to choose the channel from the intersecting set of the assigned channels at that one node, intersecting with the allowed channels at the other. This applies the other way around as well. And if both interfaces are already assigned channels, then the channel used for that link has to be in the intersecting set of assigned channels of the two nodes at either end of the link. By the end of this, we have an assignment of links to channels. There might be some links that cannot be assigned a channel, and there are two solutions to this. The first is simply to use routing to send packets between those two source and destinations. And the other option is to use that extra optional Wi-Fi link. So for the simulated annealing implementation, we start by creating a state. And a state is a channel assignment that has been developed using the algorithm just shown. Then for each state, we have to calculate the energy. The energy in this case is the objective mentioned, that is the inverse of the average SINR. In each case, we may then accept the new state or reject it or accept it based on this probability. And every iteration, we change the temperature. We have chosen to use a linear cooling function where we have calculated alpha based on the desired max number of iterations of 1000 and a reasonable starting and desired ending temperature of 0.1. For the genetic algorithm implementation, a representation of a chromosome or an individual is a channel assignment, again, from algorithm 1. And we initialize the population of chromosomes to 20 different random channel assignments. Each population at each generation is then evaluated according to its fitness. In genetic algorithm, we seek the individual with the highest fitness, and so we've used the average of the SINR, not the inverse as for simulated annealing. And then while the genetic algorithm is still iterating through generations, we perform selection, and we have chosen linear rank selection. We perform single point crossover, mutation, and then find a new population. Linear rank selection works as follows. The individuals in a population are ranked according to their fitness. Then the individual that is ranked at the top will get the highest weighting. In this case, individual 1 out of the 5 individuals will have 5/15. That is a probability of 33.3% of being selected as a parent for the next generation. Individual 2 will then be 4 out of 15 as likely, that is 26.7% likely to be chosen as a parent in the next generation, and so forth. This linear rank selection is then used to select parents, and these parents then form a new generation using single point crossover and mutation with probability of 0.5. Single point crossover means that we find a single spot at which to slice those two chromosomes. The first part of the first chromosome then links with the second part of the second chromosome, and the first part of the second chromosome is then spliced with the second part of the first chromosome. Okay, so we have used stimulated annealing and genetic algorithm to find optimal channel assignments. And we have evaluated this using simulation in Network Simulated 3. We have used node sizes, network sizes of 9, 16, and 49 nodes. Each node has two interfaces. The nodes are placed in a grid with a vertical and horizontal distance of 100 meters. Channel bandwidth is fixed at 10 megahertz. We have used the free space path loss model, and constant bitrate traffic is generated with these parameters. We then use optimized link state routing as the mesh routing algorithm. Here we present the results. In order to compare fairly the cost of simulated annealing and genetic algorithm, we have scaled with a scaling factor, and we here compare the scaled inverse of the CSIR. What we have done is we have taken for simulated annealing, we've run it for 10 different runs and found the mean and standard deviation of the final results of those 10 different runs. For genetic algorithm, we find the mean and standard deviation of the mean taken by the population of the final result. The random channel assignment is just 10 random channel assignments, and we find the mean and standard deviation of that. So we can see going from random channel assignments to simulated annealing, this is an improvement of over 7 times. And then going from simulated annealing to genetic algorithm, we have improved again by almost 2 times. We see also that the standard deviation was very large for random channel assignments and decreases a lot going to simulated annealing and then to genetic algorithm. The same applies for 16 node network. From random to simulated annealing, this is a 6.5% improvement. We can see the improvement to genetic algorithm from simulated annealing is slightly less as for 9 nodes. And then looking at 49 nodes, once again, we have a 2 times improvement here, which is less than we saw for the smaller network sizes. And then again, and 2 times improvement from simulated annealing to genetic algorithm. Okay, pictorially, for the simulated annealing plot, we plot the mean per iteration of the solution cost over those 10 different runs. And for the genetic algorithm, it is the mean of the population mean of the cost per iteration taken over 10 runs of genetic algorithm. In this case, we have run the genetic algorithm for only 50 iterations. This is sufficient to get a superior solution, but also 50 iterations of genetic algorithm is equivalent to 1,000 iterations of simulated annealing, because for each iteration of genetic algorithm, there are 20 individuals in the population, and so the mesh simulation needs to be run 20 times per iteration. We can see that even if the genetic algorithm starts off with values that are much worse than simulated annealing, it very quickly settles down to a superior solution here. For 16 nodes, the same applies that genetic algorithm, it may start off with a bigger value, but ends up with a superior solution, a lower value. However, judging between 9 nodes and 60 nodes, we can see that the improvement is slightly less. And in this case, we required 100 iterations for that superiority to be noticeable. For 49 nodes, it is clear that genetic algorithm is considerably better than simulated annealing and that it therefore scales much better. It has dropped to a much superior solution over the final solution of simulated annealing within 50 iterations and even less than 50 iterations. This shows that genetic algorithm seems to scale better than simulated annealing. The bigger the network becomes, the more marked the superiority of genetic algorithm is. So to conclude, we have compared methods for channel assignment in wireless mesh networks using dynamic spectrum access. We've introduced a new algorithm that ensures the feasibility of the solutions according to each node's allowed channels and number of radio interfaces. We've seen that the simulated annealing algorithm shows considerable improvement over random channel assignments, and genetic algorithm shows yet more improvement over simulated annealing. We noticed a slight deterioration in performance for larger networks using simulated annealing, but have noted that genetic algorithm scales better. With that, I would like to thank you and ask for any questions.